types of relations. So here we are going to discuss about the types of relations of kind 2, this is of second kind, of part number 2. In the second part, so actually there are of 5 types of relations. The first one is of reflexive, the second is of symmetric, and the third one is of antisymmetric. But here in our part 2, under kind 2, part 2 types of relations are of, one is of transitive relation, which is nothing but the fourth one, transitive relation, and the fifth one as equivalence. So we are going to discuss about the transitive relation and as well as the equivalence relation under part 2 in an advanced level. So here first of all we will discuss about the transitive relation. A relation to be a transitive one, we have to suppose a relation that is R, then 3 elements, that is A, B and C in A, in set A. If a relation is in A, if a relation R is in A, then in case if A comma B is belonging to the relation R and the B comma C also belongs to R, then that implies A comma C also must belongs to R, then only that particular relation R is said to be called as a transitive one. Then now first of all we are going to discuss about the fourth one, that is the transitive relation. Under this transitive relation, we are going to consider a relation R. Let R is a relation in set A whose elements are of A comma B comma C. Then in case if ordered pair A comma B belongs to R and the second ordered pair, that is B comma C, also belongs to R, then that implies then now A comma C also must belongs to R, then relation R is said to be a transitive relation. So here the property or the condition to be a transitive relation is if A comma B belongs to R, then B comma C belongs to R, then that implies A comma C also must belongs to R. Then the relation R is said to be called as a transitive one. Then we are going to illustrate by means of an example. Here in our illustration, we are going to suppose the property or the formula of the relation R is equals to, then we are supposing the elements as A comma B comma C as the elements of set A. Then if A is equals to B, then B is equals to C, then certainly A, first element A also will be equals to C. Then therefore this relation E is equals to will be the transitive one. Then now here let us illustrate by means of an example. So, here in the set of all real numbers, so here we are going to illustrate the first one. So, in the set of real numbers, the relation, we are going to suppose the relation as R is equal to. So, here we are supposed the relation property as is equals to, then for A is equals to B and B equals to C, then that implies A will be equals to C. Then relation R, that is equal to, is a transitive one. Is a transitive relation. So, here we have assumed the set A consisting the elements A, B and C, then the relation we have supposed it as is equals to, then now here if A is equals to B, then now B is equals to C, then automatically A also will be equals to C, because B and C are, so here A is equals to B and this B is again equals to C, then automatically all the three elements will be equals to A is equals to B equals to C, that is A also will be equals to C. Therefore, the relation R, that is equals to, is a transitive one. Then now let us consider the case number 2 under this, the illustration number 2, that is A is the set of all lines in a plane. A set A consists different lines, whereas here we are going to consider the relation R. So, here R is the relation in which the property is of is perpendicular to. So, here relation R whose property is of is perpendicular to, that too in set A consisting the different lines in a plane. Then now here for L comma M belongs to R, then we have L is perpendicular to M. So, here the lines L and M are belonging say here to the relation R, then automatically the properties of is perpendicular to, then line M will is parallel to what is a line M, and for N comma M comma N belongs to R, then we have, so here we have taken two more lines, that is M and as well as, first we have chosen L and M. So, the properties of perpendicular, L is perpendicular to M. Then now here we have chosen the second line, that is M, with the third one, that is N, M comma N, the property is of. So, here perpendicular, therefore M is perpendicular. So, here M is perpendicular to N. Then in case if L is perpendicular to M and M is perpendicular to N, then as per the property, then L also must perpendicular to M. So, here L also must be perpendicular to N, but here let us see whether L is perpendicular to N or not. So, here